Many industrial applications, like micromachining or 3D printing, require the fast and precise scanning of laser beams over large angular ranges to ensure high spatial resolution on the target as well as a large field of view and operating volume. Scanning mirrors that redirect an incoming light beam are frequently used for this purpose and are typically operated in resonance for efficient continuous scanning. The laser beam diameter requires a minimum optical aperture of the beam steering device, which often prevents the use of MEMS-based mirrors and results in an increased mover mass. To meet these requirements and provide sufficient force for larger movers, a novel resonant rotational reluctance actuator is developed. The new actuation concept locates the ferromagnetic stator parts, which guide the magnetic flux, on the side of the ferromagnetic mover, which is suspended by a torsional beam flexure. This removes mechanical restrictions on the achievable range of common reluctance actuator designs and enables the targeted large scan range. A current applied to the actuator coil generates a flux in the magnetic circuit, which entails a reluctance force, exerting a torque on the mover around its rotational axis. When the mover is displaced from its equilibrium position, this torque pulls the mover back to the position with minimal reluctance for the entire magnetic circuit. The driving current pulses are synchronized with the mover motion to sustain an oscillation at the mechanical resonance frequency and control the oscillation amplitude. In the demonstration, a laser beam is resonantly scanned over a target screen in one dimension. Current pulses with fixed frequency and amplitude are applied until the mover starts to oscillate. The controller varies the current pulse amplitude to keep the mover oscillation amplitude at a desired value. Now a sinusoidal modulation of the scan amplitude with 1 Hz is applied to the reference input, and it can be seen that the oscillation amplitude follows the reference trajectory accordingly. After switching off the driving current pulses, the mover oscillation amplitude decays slowly. In summary, the prototype system, designed for a scan frequency of 223 Hz, provides a mechanical scan amplitude of 13.5 degrees, which equals a large optical field of view of 54 degrees. With these specifications, the prototype system outperforms state-of-the-art mirror systems in terms of the product of optical field of view times the 15mm mirror aperture, which represents a performance metric with high practical relevance. Thanks for watching.